Well, happy Thursday. Let me flip over to our course here. Sorry. So we've got a couple things today. We've got to talk about the project, right? Checkers. Where did that go here? And then we need to talk about the next project, our last individual project, and then we need to finish up with our linked lists, right? Okay. Uh, cool. So let's pull up project three, or sorry, project two here, and let's get started on that. So this was backtracking recursion here. So we're going to try something, keep going as far as we can until we reach a base case. In this case, there's no more jumps, and then we're going to undo, right? Along with that, we're going to track, excuse me, how many jumps it took and find the maximum number of jumps that we could do here. So we got a couple options on that one here. So let's do project two. Right, and we get points for having a checker solver class of the constructor, takes the 2D array or vector and validates it, making sure it is an 8x8 board and then all the pieces are on the same color, right? I don't care which color. There's probably a right way. I don't actually know here. So if you said, hey, they're always on white spaces, great. If you said they're white or black spaces, that's cool too. Whatever way you wanted to validate it, it's fine here. And then being able to do this one time for one checker and being able to do it all the times for all the checkers. Turns out to do just like one extra loop. This like 5 pretty easy points for that one if you can get the first one done, right? All right, so here's our main. We don't actually need anything in main, right? Nothing required for main. We're not doing any sort of user input, but to see if your program works, we probably need to go and feed it something, either with a unit test, which would be my preference here, right? We can say, hey, I should get this number of jumps out, which would be nice, and then we leave main empty, or you maybe did it in main and just spit a bunch of stuff out here. So whatever way you wanted to go about it, it's fine here. We weren't requiring unit tests for this one here. So let's go add a checker solver. And my screen broke last night. I think my daughter did it. I might have done it here. Like the top corner over here is all black, and now the screen keeps flickering on me. And it's really sad. I have to go ship it out for repairs tonight. Class for checkers, solver, private section, and public section. So for using vector, we'll go include vector. And using namespace, using namespace standard. Great. So we've got a board, which is a vector of vector char, right? So some character, we'll call the board. That's our private attribute. And then we probably have the max number of jumps for a given board, right? I think that makes sense of storing as an attribute here. If we just want that to be the function, we could do that as well. Right? It doesn't particularly matter one way or the other what we're doing here. And then as we go, we might need to add more information here. So one of the things we can track is the current number of jumps. So we could make that a class level variable, or we could put that in one of our functions. However you want to go about that's okay. And we can come back to that part when we're done. So our checker solver here takes the vector of char the board, and we're going to go and validate it here. So if the board dot size, oh no, if board dot size does not equal 8, right, then we can rate or throw a invalid. Oh goodness, yeah, I'm going to include that, right? Include standard exception. Throw an invalid argument. Sure, why not here? Invalid board size, right? So if it's not 8, do that. Then if you want to be even fancier, right, we could check to see for int row index or just index, right? Index is 0. Index is less than my board dot size, which should be 8, right? Because we made this 8 here. Index plus plus. If the board dot at the index dot size, right? Checking the length now, right? We check we had the right number of rows. Now does each one have the right number here? Does not equal 8. We'll do the same thing and we'll throw an invalid argument, invalid board size. Cool. Now we validated this the right size. Now I need to go validate all the pieces are on the same color here. So to do that, I have to go find the pieces on the board and see are they on the right color or not. So if you take a second and look at a checkers board, I think, did we do this before we looked at one of the other puzzles? I don't know if we did or not here. So we look up chessboard here, or checkers board, whatever. Um, if you imagine these as indexes here, right? Row 0, row 1, row 2, row 3, row 4 indexes here, and then column 0, 1, 2, 3, 4. Right, as we go, let me copy this image here. We'll do a screen snip tool. Maybe I can do that. Let's grab that. This might be a little easier to look at. Oh, goodness, I have to open the snip tool. and do a new snip. New snip. There we go. Sorry. Go grab that one here. Now it gives it to me. Okay. So if you imagine those as indexes here, right, we get 0, draw, thank you. Come on. 0, 1, 2, 3, 4, on and on and on, right? And then we get 0, 1, 2, 3, on and on and on. If you add them together here, this black square is 0, right? This one, the white square is 1. This black square is 2. This white square is 3, right? Going together. So you see a little pattern. On the next row now, 1 plus 0, the white square is 1. Right? The black square is 1 plus 1 is 2. So all of the squares are either going to be even or odd. Right? The sum of the row and column indexes will either be even or they'll be odd. Right? So we can go find the first one here. So we're going to say as a Boolean value, pieces on even, we'll assume is true, I guess, or just here's a Boolean. We have to have one or the other. Right? Or you could use, I don't know, set them both to false and set one to true. That seems a little awkward here. So we'll say for int, this is the row index is 0, row index is less than 8. I can use 8 because I know it's size 8 here. Probably not a good practice. We're usually going off length this time, but that's okay. Do row index plus plus. And then we'll loop again. So that for column index 0, column index is less than 8, column index plus plus. Nope. Column index plus plus. Wow, this is not fitting. Am I zoomed in too far? All right. So if there's a piece here, right? So if the board dot at the row index dot at the column index does not equal blank, right? We're assuming there's a piece here. So if it doesn't equal blank, then we can go and set this one here. So we'll go set this value here. This is the piece that we found here. Oh, actually, here, let's do this. We'll say pieces on even is false, and then we can say Boolean pieces on odd is true or is false. So until we know otherwise, we'll say assume both are false, and then we'll go, if we find something, let's go set this one to be true or false, right? So we can add them together. So if the row index plus the column index mod 2, so we modulus by 2, right? Make sure we force our order of operations here so we don't screw this up. If mod 2 is 0, then my pieces on even is true, right? If it's not true, then it's false, right? I can set pieces on odd to be true, right? So otherwise, my pieces on odd is true. So, hey, I found a piece on an even square, or hey, I found a piece on an odd square, right? Now I'm going to loop through and check all those different pieces, and then if both of those things are true, if pieces on even and pieces on odd, we'll raise a value error, invalid board, right? This is invalid pieces, I don't know, on board, whatever we want to call it here, right? Does that make sense? So we went and checked, are they all in the same space? Lots of different ways of going about it here. This is just one of each here, right? There's not a wrong way as long as you solve the problem here. I think that works out pretty well, right? Okay, so that's our constructor. We're 5 points in of our 15 points, right? Okay, got that going. Now we actually need to go and solve the problem here. So now that I can make the board, how do I go and solve the board? So we'll write a void for solve, or maybe an int for solve, right? This would, and then we'll return the max number of jumps here, right? So eventually we'll return some max number of jumps, right? So we'll have like an int for max number of jumps. Jumps is 0 to start. We'll go do a bunch of things, and eventually we'll return this max number of jumps here. Okay, we can do that. Now, this public function here is probably not going to be useful for recursion, because it doesn't take any arguments, and I don't want them to have to go give me arguments because it makes it harder to use. Right? You just say solve or maybe get max jumps. That makes more sense here, right? Get max jumps here. We'll go do that. We can have a private recursive function that goes and has all that logic for us here. And how do I go do those steps here? Okay. Well, let's go do that. So we can have a private function here for, well, this will be int for get yeah, solver, get max jumps again here, right? Get max jumps. As long as we take some variables here, so we'll take a row index and a column index, right? We can have the row index and the column index here. Now, tracking this gets to be tricky if we don't have a class level variable. You can do it, and a lot of people who copy paste solutions from online start passing things in here, and they deal with all sorts of weird things here. I like the easy approach of let's just have a class level variable that tracks this here, so I don't need to be passing these things through all the time. Otherwise, you have to tell it, hey, here's how many jumps I currently have done, these sorts of things. We have to still manage which one is the biggest one, and that just gets to be a little bit awkward. So we'll have an int for max number of jumps, right? We'll start that off at 0, and we'll have an int for current number of jumps. Start that off at 0. So in this sequence here, we'll go through and be able to track, hey, which is the max, which we've stored once, and we'll be able to track where we currently are without having to pass them as additional function variables. Right? It's just a time saver for us, right? We could go and do it, but then it gets to be really awkward, and trying to change them here just gets to be kind of tricky here. So for this one, then, we don't even need to calculate the max number of jumps here, right? What we need to go do is go and find all of the white pieces and call get max jumps for that, right? Even this could probably just be a void function too, right? This will just take care of that for us here. We'll say, okay, so for every piece in that board here, again, we need the row index and column index because we need to pass that through. So I'll keep all of it here. And then we'll just remove this inner chunk. So if it equals a white piece here, the white checker, then we'll go and call get max jumps at that location. Right? We're just kind of skipping over the let's just do one to let's just do them all. Right? We'll give the 5 points for having this loop in here as we go. So we'll call get max jumps given, right, the row and column index here. So this function we've overloaded, we've got one that takes 2 arguments, one that doesn't take any arguments. We'll take the row index, take the column index here. Okay. Eventually, then, that will calculate whatever this class level attribute is. It'll go and set that as we've called max jump for every white piece we find on the board. Right? I don't know why that didn't show blue. That should have showed blue, but that's okay. So in here, then, we need to go and do the things. We're going to try recursing, right? Or do all of it. So if we reach the base case is we can't jump anymore, there's no work to do. So really, we just say, hey, if can jump, and where do we want to jump to? Well, for which order do you want to go in, right? With the maze solver, we did like up, down, left, right, or north, south, east, west, whatever we did. Do you want to do which diagonals first? Top left, okay. And so if jump, so then that's my row index. So that's going to start at row index and the column index, right? Column index. And then our destination, right, is going to be row index -2 to go up 2 rows, and left is -2 columns. So column index every time. Stupid collate. Column index -2. So if we can jump to there, let's go do it. Right? Again, we'll come back to add in this logic here for can jump here. Which other direction we want to try next?
Top right.
Top right. Okay, so that's row -2, column +2, right? To move to the right, right 2 columns. Right, which direction next? Down left. All right, so that's row +2, column -2 to go left, right? And then last one then must be down right. Okay, so that's row +2, column +2, right? So if we can jump, we'll go do it, right? If we can't jump, then we don't do it. So this will track each of these for us. Again, fancier solutions have like a list or a vector of these things here, and they go through each of them. Feels like a little bit of a hassle, but sure, whatever you want to do with that one here. So if we can jump, then we're going to go jump, right? This will take care of all that logic for us. So we can check, right? So we can say, hey, here's our Boolean for can jump, given a row index, int for row index, an int for column index, an int for destination row index, and an int for destination column index. So first thing we want to check is it even on the board, right? Can you go to this destination, right? So we can check, hey, if my destination row index is less than 0, or my destination row index is greater than or equal to 8, right? 8's no good. I could say greater than 7, but this way I've got 8's everywhere. I don't know. We could put that out as a variable somewhere. So that's an invalid row index, right? Or invalid column indexes, right? My destination column index is less than 0, or my destination column index is greater than or equal to 8, invalid column, right? If any of those is true, I can't go there, right? Or if there's not a piece for me to jump over. So I need to find the difference here. This gets to be a little bit awkward here. Um, this arithmetic is not my most favorite here, but we can take the difference and divide by 2, right? Or can you take that? Can you take the average? I think you take the average, right, of the rows. We'll give you the middle row, right? So we'll say, hey, if there, so we need the, this gets a little long here. So we'll say, how about if an int for middle row index or mid row index? I mean, not middle, mid row index. Uh, well, I need to know if there's a piece there. So I need to know what the index numbers are. So if I'm saying, hey, I want to jump from 4, 4 to 2, 2, where's there the thing at 3, 3? Well, I need to, how do I get from 3? How do I know what that I should be checking 3, 3 if you give you 4, 4 and 2, 2, right? So I think if we just add them up and take the average, it should give us that, right? So from 4, 4 to 2, 2 would give us 3, 3. From 4, 4 to 6, 2 would give us 5, 3. I think that's right. So we'll take the row index plus the destination row index, right? Sum those together, divide by 2, right? And integer division should be fine, right? We should always get a nice number here. And then an int for mid column index. Column index is my column index plus the destination column index divided by 2, right? So now I have got those index numbers, right? And if the destinations are invalid, we didn't even go there. So we know this will already return to true. It's going to stop because we're short circuiting. So then if we can jump then is if there a black checker there. So the next thing we're checking then is my self.board. I'm sorry, board dot at the mid row index dot at the mid column index is equal to a black piece, right? Then we also need to check, is the destination empty, right? Is there a piece to jump over? And can you actually go and land there? We know it's a valid location. It's a valid index, but let's go see. Then, right, and the board dot at the destination row index dot at the destination column index is a space, right? If all of those things are true, then yes, you can jump, right? So really, I don't need to say if true, return true. I can just return that. And we just say return this value, right? It's a little long and unwieldy, but valid indexes for rows and columns. There's a black square to jump over in the middle, and there's an open space for you to land it, right? Then yes, it's possible to jump, right? So if we can jump this direction, okay, let's go do the jump that direction. So to do the jump, then we need to go and go do that. So we're going to take my current number of jumps plus plus. Hey, we've added a jump, right? Then we need to remove the black piece and remove the white piece. So we'll take my board dot at the row index dot at the column index equals a space, right? The white piece is moving here, right? The board dot at the, oh shoot, I have to calculate the middle again. That's obnoxious. That's fine. Ugh, I have to do that every single time. It's so annoying. Someone have to calculate it again. uh, is there a way to make that easier? I don't know if there is. We can just calculate it again here. I feel bad, but that's okay. So this is row minus 2.
So how come you have initialize?
Because I've created them in a different function here, the can jump. So they don't exist in the max jump function here. We don't have those variables. Hey, maybe we'll just call. Let's just do that. We'll call jump. No, that's fine. We'll calculate it here. This is row index, column index, -2. Did I do that wrong? This was wrong here. Column and column, column and column. No, okay. Column and column, row and row. Okay. Oh, I don't even need to do all that arithmetic, right? I can just take it -1, right? Row index -1. Because I know I'm going up left. And this will be column index -1. -1. Yeah. Column. I misspelled this? Oh, 2n. Okay. Column index here. All right. So we go calculate those things here. Okay. So current number of jumps goes up by 1. Move the white piece off the board. Take the black piece at the mid row index, at the mid column index. Assign that to 0. Take the black piece off the board, and then put the white piece on the board at the destination. Oh my goodness, we need the destination now too, don't we? Shoot. um, Destination column index is row index. This just feels like so much repeated code. Column index -2, and a destination. Row index. Sorry, this row. Column index. Column index -2. We could calculate it and then just have it change a bunch, like to make it a class level variable. It would just change a bunch.
No, I'm saying like so you can instead of rewriting it sometime.
Yeah, it would have to be like a class level variable. We could go set them here as private variables, and then we wouldn't have. We still need to go calculate what it should be and set it. So I don't know if that saves us a lot of work here. Um, I'm not sure. At the destination, row index, at the destination column index here equals a white piece. Right, so this is what we're doing here, right? This is the manipulation here. Then we recurse, right? We're going to keep on jumping now. Okay, here's your new state board. Now go and jump again. So now we'll call get max jumps given the destination row index and the destination column index. Right? Now try again. Can you jump from the new position? When this is done, we need to go and undo these changes so we can try the next thing in the path, right? So we're going to go reverse these now and put them all back. I'll go one line at a time. Yeah, this is the backtracking part. So we're going to go undo that step here. Right? So now we'll put that one back to empty, put this one back to black, and put this one back to white. Right? And then take away that jump that we did here. Okay? Now, at some point we need to see, have we reached the max number of jumps? Right? So probably at the get max jumps function, we should see, hey, is this the new max or not? Because we don't need to do that every time here, but every time we call get max jumps, we can check, hey, if my current number of jumps is greater than the max number of jumps, then my max number of jumps, max number of jumps equals the current number of jumps, right? I have a new max, and we can just check this every single time. Hey, we're trying to jump from here. Are you your new longest path? And every time we recurse, we'll check again, we'll check again, we'll check again. So eventually this will get set to that max number of jumps, which is nice. So this is like do the jump, I guess, right? And then undo the jump here. So this piece here is going to be identical for every one of those 4 kinds here, right? For jump up, or can jump, down, top right, down left, down right. It's the exact same code. The only thing that's different is how do we calculate middle and destination, right? So this could be like we pull that out into a function if we wanted here, pull this one out into a function if we wanted here, so we don't have to have as much copy pasted code. I'm just going to leave it and feel bad about it here. Is that okay for now? Feels bad, man, but that's okay. So I'll just copy paste all of this here. We could come back and make it cleaner later. So if we're going top right, then our row is still -1, -1, but then our columns go +1, +1, or +1 and +2, right? Right for that. And then Everything else is the same, right? Because wherever we were, take away the middle we computed, take away the destination we computed here. Same for down left then. So down left then will be plus a row and minus a column, and plus rows minus columns here, right? And then down right, same one here. Now this is going to be plus rows and plus columns, right? Same thing. So maybe we have this. Okay, I'm feeling too bad about this now. This is awful here. Uh, so let's call this do jump here. So we'll take this out. So we have to give it all those things here, but that's fine. So we'll take all of that out here of these ones because I'm embarrassed now. I'll cut this one here. Um, or no, copy for that here, and then we'll take this one out. We'll add another private function. This is a void do jump here. Okay. Do jump needs then 6 things. It needs the row index, it needs the column index, it needs the destination, and the middles. It needs all of those values here. It'll be a little bit long, but that's okay because this will make life easy for us here. Um, column, destination, int for, oh no, before then. So int mid row index, int mid column index, right? And we can just do that same thing here from each of these then, right? So once we calculate our values here, we can use it in a do jump. We'll go and now it doesn't feel bad anymore, right? Take our current jumps up by 1, replace there, move there, recurse. So this calls the get max jumps. So we're kind of recursing between get and do, get and do, get and do, but it's still recursive because they're calling each other in this cycle here. It doesn't just have to be the same function, right? So it's technically calling a different one, but that one calls the original here. So then once we calculate all those, then we can call do jump, right? At the row index, at the column index, all those things here as we go. Now, the can jump, we already calculated one of these things here. So wouldn't it be nice to say try jump and combine those? Right? Let's try jumping that way here. So if you can do that, go do it. Right? Why not? Okay, so let's do that. So let's call this one try jump here, given the row and the column. I don't need to do any of this here. And I don't even need an if here. I'm just going to go try it. Right? Try can go figure out all of that for us. So if we know where we are, where we're going, we were able to calculate that middle point here as we go. So this will be try jump here. So then this is then if we can, we'll put back an if here. If we can do those things, right? Then we'll go do those things here, which was this one. Right? So where did our curly brace go? This was the if we can, we'll go do it here. Try jump. Now it doesn't know what get max jumps is. Oh, undefined. That's okay. So now we don't even need a do jump function here. Right? We're just going to go and try. So each one of these will be a try jump here. And we don't have to go calculate anything. Right? Isn't that a little bit nicer? Try jump. And we don't have to any copy pasted code. We feel a whole lot better about ourselves. And we feel like we're professional programmers and know what we're doing. Right? If you have the same code twice, you feel bad about yourself. It's my general rule of thumb here. Oops, where? I'll try jump, and then one over here. I'll get that curly brace. Okay, did we clean all that up then? So we're just gonna, hey, try it. If you can, go do it. If you can, go do it, right? We've got all of that in here when we try and jump. So we'll try it, and this already calculates the mid for us, which was nice with our other fancy arithmetic. And then goes and checks, hey, is it valid? Can we jump over it? And then it goes and jumps. A lot of work just to avoid some duplicate code, right? But sure, does that part make sense? Why we removed all of that here? It just doesn't like the get max jumps here. Shoot, that's a bummer here because our order is messed up now, right? What is it not? Is it because it's down below here? Checker solver get max jumps? That didn't do it. C++ is dumb here. Oh, am I missing something? Oh, I've got too many curly braces. That's why. Or not enough curly braces. Okay. There we go. I never ended this if block here. So if I end the if block, great. Okay. So our try jump calculates the midpoint, checks to see if it's a valid location. If it's a valid possible to jump, it goes and does the jump, recurses here. Eventually it'll come and undo, right? So we're able to just try jumping left to left, right, down left, down right. When that's done, it will have set the max number of jumps to the value, right? So when we call get max number of jumps here, right? Eventually it will set the max number of jumps to something here, which should be the right number of jumps. You okay so far? So I think that's it. That's the recursive bit here. That's the backtracking bit. So we're going to recurse, and then backtrack is undo. Move the piece back. Uncount your jump here. And which is great because max got set if we were the furthest along in this path, right? We just check, hey, did we reach new max? If we did, great, mark it, and then see, can you go this way, try this way, try this way, try this way, try this way, right? Let's give it a shot. Do you want to do a main function or you want to do unit tests? All right, so let's go add a unit test here. So go to.
So it's already the max number that I want to do the try jumps.
No, it's going to keep always doing the try, but every time we jump again, when we call get max jumps, it's going to say, okay, on this path you've only done 2 jumps, my max is 5. Right? Keep on trying. Maybe you'll get to 5 eventually here, right? So we got some options here. So let's go add a new project then. Add project. We'll do our test code here, native unit test project. Here's our tests. We're going to include up a directory, right? Slash project 2. Oh, are we already in project 2? Checker solver? No, we got to go up a directory. What happened here? What is this? Project 2. There we go. Project 2 checker solver. Oh, well, that other file. Those other files were in there. Okay. So to test here, test method checkered solver. Again, we should, if we wrote the code, we should test it. So it'd be nice to know if my bounds checking actually works, right? Now, this line of code will run if it's true, but we haven't really tested, hey, what happens if it's false, right? Oh, shoot, this is the opposite, right? If it's less than 0, that's bad. I had a bug. You guys gotta stop me when I do stupid things. So this is, if it is good, then, right, it has to be greater than or equal to 0, right? And it has to be less than 8, right? Greater than or equal to 0, and less than 8. And it's a B, and it's empty. Right, so if it's good, then we go, right? Because we flipped around what if we could jump or not here to this try jump here. All right, we thought that before we even ran it, right? So if I don't test the case when it's false, I don't know if it actually works or not here, right? Or I wrote a bunch of code and I never tried. We're not going to go and unit test it to death. It'd be a nice thing to do here where you try, hey, here's a negative row index, here's a negative column index, here's a negative, these sorts of things here. It's okay. We're going to make sure it works and then just know that that's something further we could do here and not feel too bad about it. Is that okay? So we got to make a board, right? So we have a vector of char for board, right? Equals a vector here. So we'll have a bunch of 1, 2, 3, 4, 5, 6, 7, 8. And then 8 of those, right? 2, 3, 4, 5, 6, 7, 8. And we got to set up a board here, right? So I think we did a couple samples in class. I'm trying to remember exactly what they looked like here. We had like a little white checker here and a black checker here. We're over one more, right? So we had to do further. Black. This was empty here, and then this one was a black checker here. I think this one was a black checker here, right? And then it would land there, and we had like another black checker here, and then like another black checker here. And what do we have? Like a white checker over this way too, or something? So we could have more than one jump path. So this should be able to do 1, 2, 3, 4, 5, right? Going either direction here. It should end up with 5. So if we wanted to check that it tests all the directions, we could add another black checker here, and then maybe like another black checker down here. So if it goes this direction, boom, 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 it can keep going here for 6. If it goes this direction first, it ends with 5, right? So we should have a couple paths. This direction just gets 2. So we have a 2. We've got a 5, we've got a 6. Right? This white checker can go 1, 2. It can go 1, 2, 3, or a bunch of different options. Right? 1, 2, 3, 4. So lots of different paths here, but ideally this one then will be 6, right? We should be able to jump over this one, this one, this one, this one, this one, and that one, right? So then we'll have, that's my board. So we'll make a checkers solver given the board. Right? Should validate just fine. So this is our arrange section here. So we're arranging, right? And then we'll have an int for expected max jumps, right? We said was 6. That's what we were able to calculate by hand. And we're going to act, we're going to call the code. So then my int for actual max jumps is my solver dot get max jumps, right? And then we're going to assert if we get what we expected. Assert equals, or is it assert colon colon? Yeah, r equal my expected and my actual max jumps, right? So we should test it out. Do you think it's going to work first time? You guys have a lot more faith in me than I have. I bet it's going to fail. We're going to get some error somewhere, right? Let's try it. Oh, see. Try jump must return a value. Oops. Oh, this can be void now, right? Because we don't need to return anything. We're not an if jump. Okay. Yeah, we had an error. You shouldn't have believed in me. Let's try it again. Let's see. Thinking about it. Uh-oh. Red. An exception on get max jumps line 91. A 91 board at the row, at the column. Why was it invalid? Were we not 8? Did I mess up? 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. It's 8 by 8, right? We didn't get an exception here. Why was that an invalid index? Did I set the board? I never set the board. Oops. This board equals the board. It would help if our board was actually existing. All right, there we go. We're getting there. Let's try it again. So the board was valid, we just never saved it. Okay, now what do we get here? Unhandled exception. What is the exception? Get max jumps 43, try jump 22? At 22, calculated in the mid. How is that invalid? Mid row. Oh, okay. So no, it shouldn't have gotten there if that was invalid though. Destination valid. Was our mid calculation wrong here? Could that have given us a bad value? Hmm. Where was that failing? Test Explorer. What did that say? It didn't tell us what the value was here. Shoot. So get at the range 32. Yep. Right. That gets to be annoying then, right? So try jump here at the row and at the column. We calculated row and column, right? Mid row, mid column, row and row, column and column. I think that's working okay, but it must not be. Let's go see. So what do we calculate those to be then? So let's put this in a try block here, right? So we'll say try here and scroll on down a bunch here this way, and then we'll catch exception E, and we can see out E dot what? This is terrible here, but that's fine. Standard. I don't have the IO stream. Jeez. Include IO stream. Shouldn't need to do that, but that's okay. All right. So I'm going to put a breakpoint here because I actually want to just pause when we get there. And let's go debug our test. So let's go to the Test Explorer, and we can debug the test. So it should pause there when that exception happens. Hopefully. See what we did wrong. All right, so we caught our exception. Our mid was -1 and negative. Why didn't this not go? So destination was -2, destination -2. So how did this get passed here? Because -2 is not greater than equal to, or, oh, I still have ors. If I and them all together, we'll short circuit here, right? This one and this one and this one and this one here, right? Thank you. And okay, I fixed a couple of the ors here. All right, again, you guys are letting me do stupid things. Let's try it again. So now hopefully this one runs here, and we don't need any of that. So let's stop it here, go back to our test explorer, run our test. Third time's the charm, right? That was our third error. Okay, expected 6, actually 3. Getting closer here, right? So we only jumped 3 times. Did I mess up my board setup here? I don't think so. So here's our checker solver. So we're trying the jump here. Okay, we can get rid of this try block because that was annoying here. Get rid of the catch and that one here. Okay. All right, so get max jumps, right? If the number of jumps is greater, set max jumps to the current number of jumps. Let's put it in here. Let's see what's happening with our board as we go. We can go debug the test here. The other thing we can do is we can just spit it out every step of the way, which gets to be fun. So maybe that's why it's nice to have it in a main here. We didn't do that for our board yet. We could represent this as a string here, or we could have like a print board function here to print it out. So we don't have to like open it up every time. But let's try it here. So let's run this in debug mode. It only gave us 3. That's interesting. All right, so the first time here, number of jumps is 1. That's fine. Okay, let's continue. Now number of jumps is 2. Let's continue. Number of jumps is 3. Okay, so we're at 3 here. Right, so we kind of have to open this up. This is where it gets kind of ugly here, though. So our board then, with 3 jumps in, looks like we've moved a couple pieces here. Right, so we started off with, what do we start off with? Which ones do we take out? So we've done, there's a white piece here. We never got rid of the original here. Right? It went here and there, right? So how did it not remove the original here? Right, we shouldn't have 3 white checkers on the board. So we did something wrong with our replace here. Right? Blank. Set it at the destination. Recurse. Set the destination. We're probably mixing up rows and columns. So that's row, that's column, 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 that's row, that's column. Okay, those ones look okay. So we put them back where they were. We end that recursion. So we started, okay, so something screwed up even earlier then, right in here. All right, let's go back to our very first jump then. Oh, I don't want to run it here. Shoot, that was not it. Let's go debug our test here. So the first step here then, here's our board. How do we get another white piece there? Where did that show up here? We have the 3 black pieces. I have 3 white pieces here. I don't even know which one that jumped. Are some of our minuses not in the right spot here? It's like we removed this. There's black piece and black piece. There's 2, there should be 3 black pieces here, but there's only 2, so we jumped one of those already? And then we ended up in a different spot. So somewhere our calculations are wrong here, right? What did we do here? So this was which jump here? At row 3, column 2. So at 3, 2, how do we get max jumps at 3, 2? Is this one? So row 3, 0, 1, 2, 3, 0, 1, 2? Is that 3, 2? Column index, row 3, column 2? How did we get here? All right, so I think we did something wrong in this one here then. Are we not calculating that right? Row index, column index, right? The board at the row index, at the column index is not a white square. Oh my goodness, guys. We need to check this. If it is a white square, we've been jumping from the wrong location here. This is part of fun you guys had debugging, right? That's normal. Happens all the time. Let's run it one more time.
Sometimes faculty say, well, you know, if you're
Hey, it passed. Okay, so 4 errors. Not too bad, right? Okay. Think that one worked. Finally, if we do all the right things. Check for actual white squares here. Now, if we wanted to remove one of these and make sure it's still calculated the right thing, right, we could. So this white square should be able to go 1, 2, 3, 4, or 1, 2, 3. Like we could go and add more tests here, right? That would be the nice thing to do. Add a bunch of other cases, make sure we don't jump off the board, do all those sorts of checks here. But at this point, I think we've done pretty good. We got half an hour left. We okay? What do you think? How'd this compare to yours? Did you all make a can jump function or try jump function, right? Nice. Yeah, it saves a little bit of time, right? Just calculate it once. Oh, you didn't do that. That's okay. Yeah, lots of ways. So having the same code's okay. Don't actually feel bad about yourself. I say that jokingly here. You can always go fix it up later, right? Spending lots of time to optimize it and take out a bunch of code is fun and all, but if it works, it works. That's okay. You don't get points for having less code, right? That's definitely not on the rubric here. So, but anytime you see the same sort of logic happening more than once, you think to yourself, "Oh, hey, this could be a function." Right? If the only thing that's different is my variables, let's try it. Right? Take care of your functional decomposition. Right? All right. So let me go post this one here on GitHub. We did pretty good. 200 winter. So here's project 2. All right, and then we'll go back to our linked list here. So where's my recent one? Open.
At least tutoring doing
Exit it here. We'll go back to linked list. So we spent some time Tuesday looking at these linked lists. This is a new way of thinking about stuff here, where instead of it being an array where I've got a fixed number of spots in memory and I can put stuff in, I just say, okay, I know what comes next. And I know what comes before me. So I can put something in at any given location really quickly. Now, the only thing that we've done is the front and the back, right? Because that's really quick here, the front and the back. But the code here is a little bit awkward, so we can make this better, right? Because we have to do all sorts of weird handling for checking null pointers, and it gets a little bit awkward, and dealing with null pointers sucks. It's a little bit obnoxious. So the way we can make this a little bit nicer and a little bit easier here is to have a dummy node that always exists. So I'll never have null pointers. And then we essentially make this thing a circle. So what we're going to do is we're going to add, every time we make a doubly linked list here, we're going to add this little dummy node at the top here. And it has null data, nothing data here. Its next is always going to be the first thing in the list here. It's always the first thing. Its previous is always going to be the last thing in the list. Right? That way we'll always have a node to exist. I don't have to bother checking for null pointers here. Life is going to be good. So to add something to the front, we put it between the dummy node and the front. It's next. To put something in the back, we put it between the dummy node and its last. Now the fun part here is when we make the dummy node, when we make a doubly linked list, circular doubly linked list, it actually points to itself. It says, hey, I'm the first and the last, because there's nothing else here. But then the logic is still exactly the same. To make a new first here, you put it in between it and what is first, right? So to add a new node here at the front here, we'll add, say, like 1, right? Its previous will be that dummy node, right? And then we tell, hey, dummy node, you now have something that comes after you. It's not you anymore, right? Now you point here. And then, hey, your new node, the thing that comes after you, is what used to come after dummy node, which was itself. So its next here then is the dummy node, right? And then, hey, thing that comes after you, I now come before you. So now we change the previous here. It's no longer itself here. What comes before this one is the first node. So the code is exactly the same because we have this dummy node here. And then to add another node, we just put it in between. Hey, if we want to add to the last, let's add a new last item here. Right? We'd say, hey, we're going to add in between the dummy node and what used to be the previous of the dummy node. So, hey, the thing that comes after you is now me. the thing is before you is what used to come before me. So now we point to here. Right? We now point to this one. And then we tell the node that comes after us, hey, we come before you. Right? You're no longer this one here. You now come before me. And then, hey, thing that comes before me, I come after you. This is no longer, this doesn't come after you, now I come after you. Right? We have this nice little circle here. I promise it's much easier. It's a little funny looking here, but this is really nice. So we copy all of this, we'll add a new class in here. No, sorry, the headers. Add a new item. This is circular doubly linked list here. So we have a circular doubly linked list here. It still uses a node has some data, has a next, has a previous. Life is all good with this one here. That's our private inner class here. We still have but now I don't need a first and last pointer here, right? I now have just a node of type T. Oh, what did I call those ones here? Why? Redo, undo that one. I have a node of type T here. We'll call the dummy node here. Okay. So now when I make a new doubly linked list here, I don't have a first and last. I have a dummy node. So dummy equals a new node, right? Of T, node of T. And its data, right, for the T data is just null pointer. Can I put a null pointer in here? Shoot, I don't know if I can put a null pointer in there. How do I put in there? That's fine. So now when I want to add the front here, I'm going to add a new node here. Its next is the dummy nodes next, right? Its previous is now the dummy node, right? Because we're putting it in between the dummy node and what used to be first, right? Because you're the new first here. Now I don't have to worry about any of these checking in here, right? I'm just going to put myself in between here. So I don't need to change first here. I put myself in, I make a new node, and then I have to go fix my links. So I say, okay, hey, new nodes, next, the thing that comes after me, previous is the new node. New node. New nodes, previous, next is the new node. Yeah. It holds the data and holds the references. So it's one of the nodes in our link. So it has these linked objects with the pointers to the other nodes. So like contains one thing, the linked list has all of them here. Yep. So we put it in between the two. It's okay. It will never be null. So before we had to say, hey, your next might be null. You can't set the previous of a next if it's null. Right? We had to do some extra checking for that. With this way, it's never null. So we can always go and set this here. So really, we're just putting it in between here. Here's my number of items. So adding to the last does the exact same thing here, except we just change around what happens. So again, I've got the same code more than once here. Feel a little bad about myself, so we could fix this up here, right? We don't even need to do this here. We'll have a add between here. So what do we want to add between? Well, I want to add the data in between. So if we're adding to the last, the thing that'll come next is the dummy node, and the thing that comes before it is the dummy node's previous. Right? Same with this one here. Let's pull this one out here. Adding to the front, then we go and add a little private helper. Void add between T data, a node of T pointer next, and a node of T pointer previous. Right? We make a node given the data. Its next is the next. Its previous is the previous. Right? Sure, you tell me what comes after you, what comes before you. I'll go make a new node, point my previous and next to those ones here, right? And then I'll point, hey, my next previous is me, my previous is next is me. Right? Fix the link so I'm in the chain here. So now I'll add between, right? And then add between should take our number of items plus plus, right? So I don't even need to do that. So adding to the front now is just one line of code. Adding to the last is one line of code, right? We add between. So add a new last, we have the data. The next one, right, should be the dummy node. I'm sorry, add front. The next one should be the dummy node's next, right? Whatever was the front node, now comes after this one. It's a new front. What comes before that one is now the dummy node, right? So adding front and adding back now are one-liners because that same logic happens no matter what, and we'll never have nulls. We don't have any special handling that we used to have here. So this is a whole lot cleaner and easier than dealing with the last one before. So this is a circular, right? Circular doubly linked list. Add last. Now we never need to check for null pointers here, right? Because we're never going to have null pointers. We don't have a first. So we can check, hey, if the number of items is equal to 0, we can throw an exception. Otherwise, we'll return dummies next data. Because dummies next is always the first thing, right? Same with last. We'll check for number of items is 0. I don't need to check this last pointer here.
You speak
Otherwise, then the last thing is dummies previous data. Right? Thing that was before the dummy node is always the last thing here. Now remove from the front. Again, we can still check the if number of items is 0 here. Now this, we've got the same code more than once here again, right? So we feel bad about this. So let's go, I want to quick actions, extract the function. Call this check empty here. We're going to say check empty. Now this can just be a private one though. It doesn't have to be public here. We'll just call check empty every time, right? Check empty. Remove front, check empty. Right? Remove back, check empty. So removing from the front gets to be a whole lot easier here, right? Because we can do all of this with one function here, right? Eventually we'll return that piece of data here. We can take all, I guess I should keep all that for a second here. Let's maybe cut all of that out here. So we cut all that and we're going to return remove node here. What node do we want to remove? Well, we want to remove the dummies next. Right? That'll be the front node here. Right? So we're going to write a little private helper function here that returns a t for remove node, takes a node of type t for the node, right? Node of type t pointer for the node. Right? So to remove it, okay, we're going to take out an item here. Now, removing the node here, it takes the node's data. The t data then is the node's data. Node data, right? Now, I don't have to worry about this first and next and all sorts of this nonsense pointer stuff here. I don't have to worry about checking for nulls here. Eventually, we're going to delete the node, right? So we'll delete the node here, which is nice. And then we'll return that piece of data. So to remove a node, then, I need to have it jump over me. So this is going to look ridiculous, but that's okay. The node's previous, right? The thing that comes before this node, thing that comes after that, is now the node's next. Right? Hey, thing that comes before me, your next isn't me, jump over me. Right? And then we do the same with the thing that comes after me. So, hey, node's next previous is the node's previous. Hey, thing that comes before me, I don't come before you anymore, jump over me. Right? Should we draw that one out? So let's put a couple nodes in here. Let me scroll down. So just put a couple nodes in the list. Yeah.
So when you're doing this, do you do like pushback or does the nodes do the node pointers automatically know that list is there?
The linked list manages all that for us, but we had it added front and add back for now because we just had that EQ deck structure. Later we'll look at positional linked lists, and that gets to be a lot of fun. We can make these a little bit fancier. But essentially, right, this is here, and there's that dummy node, right? Its previous is its previous is the last one. This gets a little funny depending on how you want to look at these here. So if this is first on the left here, its next is the first one here, and its previous is the last one here, right? And then the next of this one is the dummy node, right? And the previous of this one is the dummy node, right? Just because otherwise your circle looks a little funny. That's all. So if we want to remove the two, right? We say, hey, thing that comes before me, I don't come after you anymore. Change your next to my next. Says, okay, jump over me. Hey, thing that comes after me, I don't come before you anymore. Jump over me. Go to my previous. So it breaks those connections here, right? Breaks those links, and then we delete it. Right? That's all that one has to do. So we can delete a node, right? back, taking its data, right, jumping over it, deleting the node, right, because it's a pointer, we've allocated, and return the data. So remove from the front, then, we're checking empty, removes dummies next. That's the front here. Remove from the back, exact same thing here, right? We don't have the same code more than once here. Removes dummies previous, right? Because dummies previous is always the last thing. Okay, is empty. Now this is empty now is just going to be number of items equals 0. If I have 0 items, I'm empty. Otherwise, I have a size. We can get a given index. So now this one starts slightly differently. The code is still the same, except for we don't start at first. We start at dummies next, right? Because I don't have a first. I just have the dummies next is the first thing here. And then we're checking for invalid indexes. That should be fine here. If I have 0 items, this will still fail. I don't have that same check for empty. This is a different check here. And if the index is 0, I just am dummies next, and I never go anywhere. I don't do any of this walking here, right? We don't traverse the links here as we go. How's that feel? This is a circular, doubly linked list here. Very performant, right? We can add from the front, we can add from the back in constant time. Same performance as our doubly linked list, but now the code looks a whole lot nicer, I feel like. And we don't have all those null checks, the null pointer checks, because we have that circular one here. Yeah.
When do we use this?
Linked lists are great if you need fast add and removes. We'll get to the positional linked list eventually. We're running short on time today, where you can give. So when we used iterators to loop over vectors, and when we use iterators for we use them for our pointers. I think we did for the pointers, right? You can hold a given location. So with that idea, I can make a linked list of like 10,000 things, and maybe I'll have 15 different iterators at different locations. So I'm going to know, hey, there's 15 different spots I might add or remove from. From any given one of those spots, I can add an item in constant time. So we're going to trade off holding a little bit more memory for being able to add or remove instantly at any given location if we know what that position is. So if we've iterated to that location, I can add or remove really quickly here. So it gives us a chance to trade off some memory usage for performance here. Now, if we're just looking things up by index every single time, it's terribly slow. Don't go do this thing, right? But if most of what we're doing is adding and removing items, and maybe every now and then we look something up, but most of the time it's based on a given position we're at, an iterator we're using, super duper fast. And that's what we're doing. So we're building out, looking at some of these foundational data structures to see, hey, this is fast at this thing and slow at this thing. Right. So that's a tool we have in our toolkit. When we get to that point, we need to optimize our solutions. So we're moving a little bit beyond now, hey, just solve the problem, to how do I solve the problem quickly? Here. And then you'll dive deeper into that in 350 or algorithms analysis or data structures and algorithms analysis. Look at more data structures. Really smart people have come up with some really cool stuff. Even faster ways of doing things here. So we're sort of introing the topic, talk about our linked lists here. We're going to talk about the next project, right? That's our last project. Yeah. No, it doesn't. I don't think it gets into that. I don't think it had it last time I looked. So this was all just the supplemental stuff. Yeah, this one doesn't have the linked lists. So it talks about pointers, like your first linked list is the oh my goodness, singly linked list. Is sort of that idea here with this idea. So they have the node for nexts, right? So we know where those things go. That's all with this one here. Yeah, this one uses a bunch of pointers for things, right? So you can insert after if you have a given pointer here. So this idea, if you know where you're at, you can add before it really easily or add after really easily here with those ones. So that's their intro to it. But we take it a little further as we go here. Yep. All right, awesome. So the next project here then, let me go shamelessly copy paste a little bit here. Give me a second. Where does this one fall? Is it 3? Can you do these out of order? Yes. Okay. All right. I've been playing a lot of Magic the Gathering, so I got into that here. Thought this would be fun. So linked objects here. A lot of people like to do polynomial, but that's kind of boring here. So this one at 3:30 p.m. here for 20 points, right? Was it 20? I think it was 20. Yeah, 20 points. More options. Yeah, yeah. Submit the URL to the project, the repository, and then a README, the self-assessment using the rubric, and screenshots of it running. Okay, so not a linked list, but linked objects. So the class itself will know which one comes next here. So we're going to write a class for commander. This is the main class. This is a terrible dumbed down version of it here, so just bear with me if you played Magic the Gathering. Start at 40 hit points, and we have an attribute for first creature. So creature is the linked object. This is just the first one that we have here. It's null pointer if we don't have any creatures, or it's a pointer to a creature, right? Then we have a method for add creature, given a creature. Make sure we're doing a deep copy of this, right? If you give it a pointer, don't just take that pointer, right? We have to get all the attributes out and copy them over. Remember we did our copy constructors and all those sorts of things here. Make sure we have deep copy. Ensure the collection of creatures is maintained in order of highest defense. If the defense is the same, put the higher strength first. If both are the same, it doesn't matter. So creatures, when we add them, should be in a specific order in this linked list here, with the highest defense first. So the creature class here has an attribute for strength, should be a positive integer, an attribute to defense, a positive integer, and an attribute for the next creature, which is a pointer to the next creature. So it knows what creatures come after it here. Okay? Commander reaches 0 hit points, then the game is over. So how this works then is we're going to have some function. So add creatures, right? It's fine. And then when we battle, so we can battle one commander given another commander. Really awful version of this. I apologize here, but just go with me. So we go in order list of our creatures. The first creature battles the first creature of the other commander. So my first creature versus their first creature, right? If this fight sequence then, right, each creature when they fight deals its strength damage to the other. If the damage dealt is greater than its defense, it dies. Remove it from the collection. Both creatures can die. They could kill each other here, sure. One creature could die, or no creatures could die. So if my strength is higher than their defense, that creature dies. If that creature's strength is higher than my defense, I die. So the creature fights. Or just one of them dies, or none of them dies. If there's a remaining creature, and all of one commander's creatures are dead, now their first creature is a null pointer here. The remaining creature strength is dealt to the commander, and the commander loses hit points. So if you have no first creature, or I killed all your first creatures, all the rest of mine deal their strength damage to that commander. Okay? If both creatures survive, the fight's done, nothing happens. So if we both have low strength but high defense creatures first, nothing happens. Right? So 3 things can happen. The fight stops when both creatures survive, or one commander takes damage from the other creature, or both commanders are left with 0 creatures. Right? So either both of our creatures survived that round, or one of us took damage from all the remaining creatures here, or both of our creatures died and we have none left. And one of those 3 things will happen. So that's like, here's the fight round that happens. And you don't actually need a main function here. You don't need any of that. We're just having the logic. You probably want to write one or write some unit tests to make sure this stuff works. Okay? It's a little nonsensical. I apologize, but just practicing a linked object. So dealing with the creature that knows its next creature. Dealing with the creature that knows its next creature. So the commander has the first pointer, right? Like our singly linked list. It had the first node, and the node knows about the next node, knows about the next node, knows about the next node. But now we're adding some attributes and going to do some logic with it here. We're going to keep those in descending order of defense. You want your highest defense creature first to take the most damage, right? So when we go and add them into the list here, if it's a higher defense, add it there. If it's not, go to the next one, right? If it's not, go to the next one. Eventually, you either have a null pointer, there's nothing next, right? Or you found where you go in between, right? Yeah.
If all creatures are holy strength in the
No. So only your creatures will do damage here. Okay, so your commander class is going to be 5 points here. Oh goodness, commander class is 5 points here. This copy paste is the worst here. And the creature class is 5 points. And having add creature does a deep copy and make sure we stay in the right order. It's 5 more points. So just having the class gets you the points. Having this actually work is 5 more points, right? And then the last one is the attack function here, commander attack function actually does what it's supposed to do here, right? So 20 points for this one here. If it doesn't work, you can still get a lot of points, right? You get points just for having the class here, points for having the class here. If it sort of works, you get partial points. If it sort of works, you get partial points. Right? Again, get started, get me something. You're working on it early. We got 2 weeks to work on this one here. Linked objects are a little weird. Dealing with, hey, here's my current one. Here is the next one. Is the next null or not? Gets to be a little bit awkward. But that's why we're going to practice it here. So we get familiar with using pointers, going to the next pointer here, making sure it's not null, those sorts of things here. The actual logic itself is kind of stupid, right? Hey, check your strength, check your defense, see which one's greater, those sorts of things. So we need to be able to remove creatures. We need to be able to add creatures, right? The remove bit's kind of implied that will happen when you're fighting. If your creature dies, it gets removed, right? So we need a way to remove. There's no points for that because it's part of this attack function here has to go and remove creatures. So that's implied you'll have a way to remove a creature from a list here. Okay, that makes sense. So you can use singly links, you can use double links, whichever way you like here. Double links are nice because to remove it, you know what comes before and after you already, right? That's an option here. So you're welcome to do that. You're welcome to use a single link here. So it says, hey, it has to have at least a next here. You can do that one here, right? And if you want to add the previous in, you can. And you're welcome to do more, but this is the minimum here. Okay. All right, cool. That's all we got for today. So we will come back next week, right? Let's see. Let me double check what we're doing again here because I can never remember. Yes, the midterm review. So let me give you, I'll just add it here. I've got the other class open actually here. So let me pull up the midterm from then. Go to the midterm here. And I did post the quizzes, right? Did I tell you guys about that? I didn't put a due date on them. You want to have looked at them before you take the midterm, right? Because the same kind of questions will be half the midterm here. So it's 15 short answer questions and then 3 long answer questions. Ideally, you could take it in an hour and 15 minutes. I don't care to watch you take a test. I don't need to watch you take a test. Not everyone tests well at 3:30 in the afternoon, right? I particularly have my coffee slump where I start to get really tired at 3:30. It's a bad time for me. So it's open book, open notes, open internet, not open neighbor. Don't get on group chat, please. Right? This should be easy. If it's not easy, you and I need to talk. Right? This should be pretty easy for you here. So we pull up this last midterm. We'll go preview it here. So you agree to follow the academic integrity policy. Again, they did some research on this. If you agree ahead of time, you're less likely to cheat. Then at the end, you say, oh, yeah, I acknowledge I didn't cheat. You're more likely to be like, oh, I cheated. What do I do now? Crap, I'm just going to say I didn't cheat. So sure, you get a free point for that. And then some questions here. Again, we'll go over these next week. We do the midterm review itself here. And then long answer questions here. We'll have 3 long answer questions. So one of them will be on recursive functions. Right? It'll be a different version of this. But here's a recursive function question, right? That does something. Okay, so here's one example. It'll be like this, but with different words, a different kind of recursive function. And then another question on 2-dimensional vectors. Do something with the 2-dimensional vector, right? And then the third question will be on writing a class and then using inheritance to override something here. Okay, so those 3 questions. Ideally, I aim for these to take about 10 minutes. So that if it does take you double the amount of time, you still would be able to finish this all in an hour and 15. Sometimes I'm a little off on my estimates here, but essentially the idea is I figure out how long it takes me to do it, and then I triple it for you guys. So I think this is a 3-minute question for me, right? That just for a scale here, right? This is not super long, right? It's got some names and attributes, get methods, it's got a constructor, sure, and then we extend it here. This is like 15 lines of code. Right? There's not a whole lot happening here. That's all. Okay. So I'll export this out, or I'll print it as a PDF. Actually, it gets super long because they're all long answer questions, but that'll be okay.
So,
Yep. So it'll open 3:30 next Thursday, and then it'll be due the following Tuesday by 3:30. So whenever you can open it, read it, fall asleep, come back to it, have your shower aha moments, and like you solve code, that sort of thing here. So let me go add that to files here, and I'll go upload that one here from my desktop. There it is.
3:30 Thursday.
It'll open 3:30 next Thursday. Yep, and it won't be due until 3:30 the following Tuesday. So untimed. Yep. All right, any other questions? All right, awesome. You folks take care. I will see you Tuesday.